we've just introduced the concept of a function. And what we want to do is to study these in great detail. We want to look at specific examples of functions. We want to look at general properties of functions, because functions are going to be the foundation of everything you're going to do in your lower division classes in mathematics. So just kind of informally, to describe what a function is, rather than write down the formal definition, which kind of takes a little bit of time, a function essentially is a relationship between two quantities of a very specific form. So it's a relationship between two quantities. So this isn't a precise definition, but I'm going to call it x, which I'm going to call the input, and the output, which I'm going to call f of x, often shortened to y. So this is the output. So a few things to be said. This is called the, where am I? So the x is called the independent variable because it's kind of the input, and you're free to choose what the input is to some extent. So this is the independent. And f of x, it's a number as well, and it can vary, so it's the dependent variable because it depends on x. And something to say, the inputs and outputs, each input is assigned exactly one output. You can't have more than one output for a given input. Each input assigned exactly one output. So you can't have a situation where you have two potential outputs for a single input. That's not allowed. That's not what a function is. For example, the function where I took a positive number and I said I want f of x to be the square root of that number. That can't be a function because there are two possible square roots. There's a positive and a negative. You can make it a function by essentially saying I want the positive square root. Then there's only one. That's totally fine. But that's important. Okay, so it's some sort of machine or rule which, given an input, gives an output. And the allowable inputs are in a subset of the real numbers called the domain, which is part of the information of the function, really. So it's quite an abstract idea. So the aim, basically, as I said, is to really understand functions in a lot of detail. And the thing is, functions kind of turn up in lots of different scenarios, and we want to be able to look at them from different perspectives. So the aim is to find a sensible way to represent a function, or find sensible ways to represent a function. So it's a lot of data, a function, really. Okay, it's a domain, and for every point in the domain, it's some output. Every x has an f of x assigned to it. So it's a lot of information. And a general function is kind of a free-for-all, really, right? There's no reason that there has to be some sort of coherent overall plan. You could just make a random choice of f of x for every single x in the domain, so it just could be all over the place. But really, we're only going to look at functions of a very particular nature. So the first way that we could describe a function would be verbally. So I could give you a kind of a succinct description of what the function does. So I'm going to give us 4 different ways that we can kind of sensibly-ish talk about functions. So verbal, here's an example. I could just say the function that squares a number. The function that squares a number. Now that is a function because it's a rule. Like given a number, or given an input, a number gives me an output, namely the square of it. So this is very succinct in this situation, but it's it's a bit opaque, right? It doesn't really tell us a huge amount about the properties of the function necessarily. So this is succinct, but in all likelihood is too succinct. It can't really tell us very much. Succinct, but probably, I mean, in this case it's so simple, but in a more complicated example it may not be very useful, but probably tells us little. Another way of doing it, well, if you want to think like a computer, a really good way to think about a function is with a table, where basically you list all the possible inputs and then beside them list all the corresponding outputs, right? So that's a perfectly reasonable thing to try to do. So we'll say with a table. So let's do an example. So let's keep the same function going. So the function that squares a number. So what I could do would be to kind of express that a little bit like the following. Could say, so I'm going to draw kind of a piece of a table. So 2 columns, x here, f of x here. So just as an example, I could have a 1 and then 1 squared, which is 1, a minus 1 squared is 1 again, 2 squared is 4, 6 squared is 36, dot, dot, dot. Now, the problem with this, obviously, is it's not going to be able to capture everything about this function I'm describing. All it's going to tell me is a discrete collection of inputs because it's a table, right? We can only have a finite number of columns. So this is very kind of concrete, but it's limited. So only tells us f of x for a small number. Of x, right? That's the problem with this approach. I mean, the table could be massive, right? It could be a million rows, but that's still not everything, isn't it, right? Because the thing about this function squaring is the domain's all real numbers, because I can square anything if we're using our usual convention of saying that the domain is as big as possible. So this is good, but it's going to be kind of limited in what it can tell us. One thing that I will say is tables are incredibly useful when it comes to describing functions which are coming from experimental data. In fact, almost always this is how experimental data would be described. So very, very effective for functions coming from experimental data. Coming from experimental data. Or indeed just functions which have limited information. So if I'm measuring, I don't know, the temperature at given moments in time, perfect, right? I measure them every 5 seconds, build a table, right? A really nice way to do it. But it's the kind of thing you can tell a computer, but it may not be terribly illuminating about the behavior of the function overall. So this is a useful thing to do, obviously, but it's pretty crude. It's just like dumping all the information without sorting it particularly well. So another way to deal with this would be another way to represent a function would be with a formula, something I'm sure that you've all seen before and we've already talked about to some extent. It was the first example we really looked at. So a formula. So as an example, if I was doing the running example we've got now, this squaring a number, the example would be f of x is equal to x squared. That is a succinct way to describe the function. So this is great for several reasons. The first is, I mean, it tells us very precisely what the output of the function is for every single input. So it really tells us everything. So this tells us the output, I'll just write this, tells us the output for all possible inputs It's a really great way of describing the function, right? It really is crisp, precise. So this is precise and it's powerful, as we're going to see. However, I mean, it's beautiful and succinct, but it may still not make it completely obvious what the basic behavior of the function is. So if I give you some really elaborate formula and I say, is the output of the function positive or negative, for example, you'd be like, oh my goodness, I'm going to have to do sign analysis on this, which is going to be difficult potentially. So it could make understanding more fine properties of the function difficult. Could make understanding properties of function difficult. It's still a really good thing to have, don't get me wrong, but if I give you an elaborate formula and I say, well, what basic behavior does this function have? What are the possible outputs? What's the range, for example? What's the domain? It can still be very difficult, even though you've got this nice formula. So the final approach is a very visual approach, namely the concept of the graph of a function. And this, in conjunction with the formula, is certainly the most powerful. So I don't really want to get into huge detail about what the graph of a function looks like in general. We will talk about it as we kind of go through this course, but let me do this example. So I think kind of the graph of the function is in many ways the most powerful way to represent the function because it gives you an extremely visual sense of what's going on. So the basic idea is, well, you want to represent the information of a function as pairs of numbers, right? So an ordered pair where the first one is the input and the second one is the output. So x followed by f of x. And the beauty of this is if you take the xy plane, right? So the ordinary plane with xy coordinates, so Cartesian coordinates, if I give you a pair of numbers and I write them kind of as one followed by a second, so an ordered pair, that represents a position in the xy plane. So what I could do is take the xy plane and just mark in all positions where the relationship is the one given by the input-output relationship of the function, and that's what the graph of a function is. So let's draw kind of a simple example, or this example. So if I draw the xy plane, label x there, label y, oh sorry, label y there, and then x here, and I mark in all positions where it's x comma f of x. Well, what will happen is it'll build up a picture that looks like the following. So this is something I'm sure that all of you have seen to some extent, stretching off with this kind of pattern. Okay, so this is algebraically written down as y is equal to x squared. And what that means is if the x coordinate is x, then the y coordinate is x squared. So just as an example, if I had the position, let's say 2 down here, so that's kind of the 2x coordinate. If I was to match it up here, it would be 4. I know the scale's a little bit off, but that's the basic idea. And more generally, if I chose just a general x here, then this position, the y coordinate, would be x squared. So I'm not going to define what a graph is of a function in huge detail now, but this is the essential idea. So we mark all positions in the xy plane and with this blue coloring. So I'm going to do x comma f of x, but that's x comma x squared in the xy plane. That's what a graph is. So a graph is an incredibly powerful way to look at the function. It tells us a huge amount of stuff. For example, I can look at this graph and instantly tell you that the output of the function is always non-negative because the y coordinates of all of these B points are positive. right? So it's above the x-axis. So that immediately visually shows me it has to be positive. We're going to see that many important properties of functions are very easy to detect if you have the graph in front of you. So this is extremely powerful, right? This is a very effective way of representing a function. So it's a very effective way of showing the general properties of a function. But it's somewhat imprecise in the sense that if I just show you a picture, then it's difficult to know what the formula is for it. There's no guarantee at all you'll be able to find it. So it's a little bit imprecise. Somewhat imprecise in comparison to having a formula. A formula is extremely powerful. If I give you the formula, then I can, in theory, write down the graph, right? It may be incredibly time consuming, but it could be done in theory, right? You know abstractly what it would mean. You just mark all the points x comma f of x. You can't really go backwards from the graph though, not in general. So the graph is extremely powerful because it gives us lots of kind of general, it will give us lots of general information about a function, but it's a little bit imprecise, as I said. So really the most potent way to represent a function is a combination of a formula and the graph. If you have both of those, you're really cooking, because the formula will allow you to do really precise work with the function, and the graph will really tell you the broad behavior of the function, kind of important things that may not be completely obvious from the formula. Okay, so I want to think a little bit about the graph and what it is about the graph, or some visual properties of the graph that guarantee it comes from a function. So observation. So this isn't really to do with functions. Algebra and geometry are very closely related. And what I mean by that is if I give you some equation involving, let's say, x and y, so some relationship between x and y, I don't know, x squared plus x times y is equal to 4, something like that. Then I could mark in the xy plane all positions x comma y which satisfy that constraint. Just like up here, I've marked all positions in the xy plane where the constraint is y, the y coordinate is equal to x squared, where x is the x coordinate. But if I give you a more general formula, not of the form y is equal to something in terms of x, just any old formula, I can do the same thing. So this is kind of a fundamental relationship between algebra and geometry. It's kind of one of Descartes' great insights. That's why it's called Cartesian coordinates. So any equation involving, let's say, x and y, will give a curve, if you want, in the xy plane. We'll give a curve in the xy plane. So it's all positions x comma y which satisfy the constraint given by the equation. So I think let's do an example. All right, so here's an absolute classic example. Let's take the equation x squared plus y squared is equal to, let's say, 1 squared. Now I know it's equal to 1, but let's just put it there. So imagine I needed to work out all the positions x comma y in the xy plane where this equation is satisfied. So let's take a moment to think about this. We got y, we got x. Okay, so I'm just going to think this through a little bit, right? So if I choose a position here, x comma y, all right, and I want it to satisfy this. Well, let's make a really interesting observation. If I was to drop a straight line down here vertically at right angles, then what would I have? I would have this length here would be x, and this height here would be y. And now notice, if I was to draw a straight line out to here, what would happen? Well, if I draw a straight line out to there, I know x squared plus y squared has to be 1 squared. But that's exactly Pythagoras' theorem for this right-angled triangle. The square of the hypotenuse is equal to the sum of the squares of the other two sides. So if this is true, and x comma y satisfies this, this has to be 1. So that means the distance from the origin 0, 0 to xy has to be 1. And it turns out that actually works not just for x and y positive, it'll work for any x and y at all. Namely, the x comma y which satisfy this constraint must be exactly distance 1 out from the origin, all the way around. But what's that? That's a circle all the way around. So the xy coordinates by Pythagoras' theorem are all the points exactly distance 1 from the origin. So that means if I was to draw this curve, it's going to be a circle centered at 0, 0, so the origin of radius 1. So let's try drawing this in properly. So this is just a really beautiful piece of, well, it's a combination of several things, Pythagoras' theorem, algebra, geometry, so it's nice to see. So if you've not seen it before, this is a great time to see it. So if I take a circle of radius 1, that's exactly the points here. Okay, so if I was to, I'll do kind of the marking again. If I take any point, x comma y, exactly as I said, the distance out has to be 1 by Pythagoras' theorem. And that works all the way around. It doesn't have to be in the first quadrant. Very nice, right? So this is a circle of radius 1. Centered at the origin 0, 0. A circle of radius 1 is often called a unit circle. A unit circle. So just to kind of reiterate, Pythagoras gives the equation. Very nice. Okay, so I have this piece of algebra, this equation involving x's and y's, and it's turned into a piece of geometry, right? This is a really profound idea in mathematics. The fact that algebraic things have geometric interpretations. All right, so very neat. Here's a question. Does this come from a function? Is this the graph of a function? Well, let's have a careful think about this. So let's take the same basic picture. And go down here. I'm going to take the same basic circle. I'm going to remove all the mess from around it. So, warning. So I'm kind of going to jump the gun here. This cannot actually be. This cannot be the graph of a function. Okay, so y is equal to f of x. It can't be that. Now, why not? Well, let's have a moment to think about this. Imagine I was to have, if this was the graph of a function, and I asked myself, okay, what's the output for a given input? So what would I do? I would choose some x. So I've got 1 here, got a -1 here. I would choose some x between -1 and 1, so choose this guy here, let's say. Then what do I need to do? Well, I need to work out the positions which have this x coordinate. So I suppose what I'd do is I would draw a vertical line through this. But now something pretty serious has happened. This vertical line has hit in 2 positions. So if this were the case, this y coordinate would have to be the output, but so would this y coordinate. So if this was the graph of a function, f of x would need to take 2 values. So this would tell me there would have to be 2 outputs. So f of x would have to take 2 values. And that's not allowed. Right? You can't have f of x as 2 outputs. So the fact that this vertical line crosses at 2 points messes everything up. So geometrically, I can see that this vertical line has been very useful to me, right? Drawing this vertical line, having it cross at 2 points, or intersect at 2 points, has messed everything up. And I can actually see this algebraically as well, which I think is good practice. So how could I have spotted that there's a problem here? Well, if this is of this form, I should be able to rearrange it to get y is an expression purely in terms of x. So if you want to do it in a bit more primitive terminology, we should be able to solve this for y in a reasonable way. So if I do this, what happens? Well, we would have y squared. So I've dropped the square here because it's not necessary. We've got y squared would be equal to 1 minus x squared. Sounds good. But then I would take the square root of this, wouldn't I? And the problem is if I take the square root of both sides, in fact, I'm going to do this extremely carefully for you. I think it's really good to be super careful. So that's all good. Square root of both sides, but then what? Well, now here's the problem. The square root of a square is the absolute value. And that means the actual value of y could be plus or minus. So there are 2 possibles. So what you're actually picking up here is the following. This algebra is picking up the fact there's a problem. And the plus is picking up this guy up here. So maybe if I want to do this guy, so the y coordinate here, that's equal to the positive square root, which by convention is this, remember? And this guy down the bottom is the negative square root. So it's minus of this guy. So you're picking up the plus and the minus. So algebraically, we could have seen something bad was going to happen, right? It's not possible to rearrange this. So the output of the function has to be unique, so this is no good. So this is something really interesting, right? This is telling me if I was just to draw a random curve in the xy plane and ask, does it come from a function? I'll be able to use vertical lines to determine if it is or not, right, pretty quickly. So this gives rise to a really slick way of using the xy plane, really, or the graph approach to determine if a curve comes from a function. So this is called the vertical line test. Vertical line test. So if I give you a curve in the xy plane, so just any old curve, is the graph of a function let's say y is equal to f of x, if and only if the following is true. Any vertical line intersects the curve at most once. And it's at most. It may not intersect it. At most once. So this is called the vertical line test because it gives us a good visual way of checking if a curve actually does come from a function. So let's do a few examples, shall we? So if I gave us the xy plane, and I draw some sort of curve, let's say it's got a fixed endpoint here with a solid dot, not that matters too much, and something like this. Dot, 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 going off in this direction. All right. Does this come from a function? Is this y of f of x for some f of x? Well, if I draw a vertical line, what can happen as I move it around? Well, from the way I've drawn it, I don't intersect over here, but I suppose that would just mean that x over here isn't in the domain. There's nothing wrong with that. But over here, I am getting corresponding x coordinates, or points with these x coordinates. Am I getting one output? Yes. Because when I cross, I only cross once. I don't have any ambiguity about where I cross. So in this case, no intersection, but if I'm over here, one intersection. So the vertical line can cross at most once. At most. It may not cross at all, but it doesn't matter, as long as it doesn't do it more than once. So it's perfectly possible to have no intersection, as here, and here, just one intersection. At this point here, for example. Exactly one intersection. So let's do a non-example, another non-example. So if I have some curve again, x, y, I don't know, something like this. I mean, I can do anything I want, but let's not go too crazy. There we go. It's a pretty mad curve. That thing there. Does that correspond to a function? Well, I remember what the statement is. We take a vertical line and we see where it intersects. I need to make this one a bit longer, I think. So I see where it intersects. Now, be careful. The vertical line test says what? Let's zoom out a little bit. It says any vertical line intersects at most once. Not some vertical line intersects at most once. So over here, down this guy, yeah, I'm only intersecting once, all good. Same over here, all good. To these x, I get one output. But the moment I go into here, big problems. I cross a bunch. So just as an example, if it was this position was my choice of vertical line, what possible outputs would there be? Well, I'd have three options. That, or that. So this guy has three intersections, this specific choice. Three intersections. This implies there is no single output. If there was a function, this implies not the graph of a function. So the main thing is all it takes is one to go wrong. Is one vertical line to fail. Doesn't matter if a bunch of them work, it's got to work for all of them. The moment it doesn't work for a single one, it's no good. And maybe just to go back up here for a second, this guy does fail the vertical line test. Absolutely, right? But you do know, so this really comes down to the fact that square roots are not unique. That's the problem here, right? When you take square roots, there's two possibilities. But we have talked about the fact that if you take the positive square root, it does become a function. Well, that actually works really well here. So let me just show you what I mean. If I was not to take the full curve given by x squared plus y squared, but instead was to only look at the stuff which is above the x-axis. So if I kind of cut this off like this. So if I just look at that. Now, if I just look at that, that is the graph of a genuine function. It's the graph of this function, right, where it's the positive square root. And does it satisfy the vertical line test? Well, yes, it does. Because any vertical line, I basically removed the problem case at the bottom. Any vertical line, any vertical line crosses at most once. It may not cross at all, but if it does cross, it only crosses once. So this is just something to bear in mind. It's a really nice example. So just to recap, functions, quite a complicated idea. It's an awful lot of information in a function. That's the thing to understand. It's a huge amount of data. You've got the domain, then you've got all the information of all of these inputs and all of these outputs. So it's like a whole big machine. So finding ways to represent it's important because it's just a huge amount of data. You could do it verbally. It could be succinct. It could really tell you exactly what's going on, but you'll be lucky for a complicated function if you can do it well. With a table, very numerical, good for a computer, pretty crude though, and it will only ever show finite amounts of information. Formula, super precise, powerful, especially when you're doing calculus, having a formula is incredibly powerful, but it's a little bit opaque. You can't immediately see things like domains or ranges and all the rest. Finally, a graph, which is a bit more sophisticated because it's a blending together of algebra and geometry, but it tells you an awful lot just from the get-go. Looking at a graph, it tells you the basic behavior of a function in ways that none of the others do, even a table. And the beauty of a graph is you can determine if it comes from you can determine if a curve in the xy plane comes from the graph of a function by doing the vertical line test. So any vertical line, if it crosses once or not at all, it's the graph of a function. But if at any point it crosses more than once, it's not the graph of a function because it would have to correspond to two outputs.